binary search tree. Okay, we call this a BST. Okay, so this is a binary search tree. Okay, and that video was pretty good. Probably the most important topic in computer science, because it's really cool. All right. Okay. So based on the video from yesterday, tell me about what you learned about a BST, binary search tree.
He was saying that it's an O of H time.
Oh, an O of H time. Yeah. An O of H. Yeah. Okay. And what was H?
I don't know. I was confused.
What was that? The height. Yeah. So H is the height. Okay. All right. So O of H. All right. And I will define what do we mean by height in a second. But in the back of your mind, be going, wouldn't it be nice if that was an N? Yeah. No. It's not O of N. It's O of the height. And we'll see that that turns out to be log N, which is really nice. Okay. All right. Because then we can search, update, delete in O of log N time rather than O of N, like that linked list and all that stuff. Okay, all right. So, all right, anything else that you learned about?
Traversal order.
Traversal order, yeah. What traversal orders are they?
It's like the left to right.
Okay, we got lefts and rights. There's 3 traversal orders. What? Oh, an iterator? Yeah, he did stuff with iterators. Yeah, we're not going to do that. What? Yeah, we have sorted order. Okay, so I'll just tell you what they are because I'd sort of label them a little bit different. We have pre-order traversal, pre-order, in order, otherwise known as sorted order, okay, and then post-order. Yeah, I'm going to have to put off the lab. There's too much cool stuff I have to teach you before we start playing with the code.
Pretty sure the code space is messed up too.
Is it messed up?
Yeah.
All right. Okay. Okay, so those are the traversal order. Okay, what else did you remember?
Successor,
The
successor.
order of them.
Uh-huh.
There's a parent, there's a child, there's successor.
Okay. Parent, child. Okay, let's talk about a node. So let me just draw a node here. Here is a node. I'm going to draw it like this. Okay? And what? What?
You use circles. In my mind, it's going to be circles, and then you draw a rectangle.
We're doing it this way.
Because of the pointers.
Because of the pointers.
Yeah.
Yeah, because of the pointers. Okay? And the other reason why I'm doing this is last week I had a ding, 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 a linked list, right? And if you noticed last week's video, I also drew them in sort of a 2-dimensional shape, which turns out to be a tree structure. Okay, all right? So really, a binary tree with no S. A binary tree is a tree where each node has 0, 1, or 2 children to it. Okay? All right. All right. Anybody from math know the definition the difference between a tree and a graph? No. All right. What's a graph?
Are those doubly ended arrows?
Are they doubly ended?
Yeah, they point up.
I don't want to do that yet.
Okay.
Code gets very messy. Very messy. We're not going to do that. So just like we started with linked lists and the arrows only went one way, and then we said, would it be nice if we could go backwards? And then we added the backwards arrows, and the code got more complicated. Yeah. So we're going to do a simple binary search tree without, we call them parent pointers, that point back to the parent so you can go back up the tree. We're going to get away with singly, only arrows going down, probably for a while. Okay, all right. As long as you understand, I could go back up if I had parent pointers. That's great. Last year, I did not have a lab doing that because the code just gets more complicated. It doesn't really gain you a whole lot. because there's some recursion tricks that you can do so you don't have to go backwards. You can do it in functions. Okay? All right. All right, what is a graph from math?
They're plotted points.
No, a graph, not like a plotted points. Oh, okay. A graph is a set of edges and a set of nodes. And you have edges between nodes. That's almost fully connected, isn't it? We got to make another one that's weird. Let's do that one. Okay, all right. What does this look like to you in real life? What would we have? Nodes and edges. All of us drive on roads, right? So I could sort of model this as being an intersection. A node is an intersection, and each of these are roads that come off of an intersection. Okay, all right, now in algorithms, what is that, CSCI240, we deal with graphs a lot, and then we figure out how Google Map works, and we write a miniature Google Maps that does this. It traverses the graph between two nodes, okay, the shortest path in the shortest amount of time, and all that fun stuff, okay, all right? Now, if you sort of look at it based on the video you watched, technically, there is a very strong relationship between a tree and a graph. All right? Now, a tree doesn't have cycles. And what that means is, if you notice over here, I can drive in circles. Circle, 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 circle. Okay? All right? A tree is a graph that doesn't have cycles. Okay? So you can't do circles in it. Okay, all right, and we typically draw a graph like this. Draw a tree like this, and what do you call the top node? Yeah, did anybody notice the t-shirt he wore yesterday in the video? I need that t-shirt. Yep. All right, and we put the root of the tree at the very top. All right, is there any other, can I label any other features of this? Leaf, yeah, what's a leaf?
If it doesn't have any children.
Right, if it doesn't have any children, this is a leaf node. Okay, we're going to label anything else. Oh, by the way, how many leaf children are there? In this picture, 3. Yeah, 1, 2, 3. All right, and what is the parent of this one? That one. What is the 2 children of this one? That one and that one. Okay, all right, so we have the sort of the parent and child relationship thing going on. All right, we have the root node, and the next definition is I want to define the height. Okay? And the height of a tree, and this is my disclaimer, I learned it one way. If you look at some books, they give it a little bit different way, but I like this definition, is the height of a tree is the number of edges on the longest path from the root to the deepest leaf node. Okay? Number of edges. Okay, all right? Other definitions are the number of nodes on the longest path. And if you notice, those are different numbers. Okay? Because if you count the nodes, you get 3. If you count the height with the edges, you get 2. Okay? All right? Now, I don't know. In this course, we're going to go by edges because it makes our life easier. Because to me, for anything to have any height, it must have a branch coming down. Otherwise, it's just a point in space, and that doesn't have any height because it's just a point in space. That's what makes sense in my mind. Okay, all right? So if you're online and you notice like you're off by 1, and notice the height of this is, I would call this 2. Some places would call this 3. Okay, all right? So in my unit tests, I'm using this to net definition. The height is the number of edges on the longest path from root to leaf, or to a leaf. To leaf. Yeah, okay. Anyway, it's this one. It's the deepest leaf. Okay? Okay? All right, so what do I get this? All right. Was there any other definitions that he defined in the video?
The depth and height.
Yeah, so, yeah, the height. Yeah, what is the depth?
Being opposite.
The opposite, right?
Yeah. It's the opposite, right? So what is the depth of the root node? 2. Depth, depth, right? Sort of think of it going up, okay? And here we have this big O of h, which is the height of this, all right? And in this case, I have 1, 2, 3, 4, 5 nodes, and what's the height in my definition? Yeah, 2. Okay, yeah, I got 2. Okay, all right. Okay, did he go into the math and show why it's log n?
Because he said it's like.
He waved hands?
It wasn't in that class.
It wasn't in that class.
We'll do that next class.
Yeah.
Ah, okay, all right. Well, I will show you right now. Okay, all right. So let's take a look at some trees here. This is way too much fun. Let's back up. Let's back up a second. Let me just talk about the S, the search, binary search tree, which is really that quiz that I gave you. Okay, all right. So if I wanted to insert the numbers, I'm just going to do what was on the board: 4, 3, 2, 6 into a binary search tree. What do I do, and what's the rule that he talked about in the video? By the way, do I have any binary search trees up on the board right now? So it's empty, right? Okay. So the first thing that we're going to do is we're going to insert the node 4. Okay. Oh, I'm going to fall off my diagram like this, but that's okay. I'm just going to write numbers in lines. Okay. The next element we're going to add is a 3. Okay. Now, there is already, I'll make this sort of pointer-ish. There's a root pointer that right now points to the node 4, okay? And if I were to insert the node 3, where does the 3 go? Off of one of the children, okay? All right? So which side? The left. You did that backwards on your homework assignment.
Did I?
Yeah. All right, so I'm going to put the, as long as you're consistent, I don't really care about the left versus the right, but it makes sense in my head if the smaller numbers are on the left and the bigger numbers are on the right. Okay? If you write it backwards, the math works exactly the same way. It's just you got to flip the paper over. Okay. All right, so now we have a 3. All right, and what about a 2? All right, so what's the rule? The rule is smaller numbers to the left, bigger numbers to the right. All right, so if I'm sitting on the 4 and I want to insert a 2, is 2 going to be on the left-hand side of the 4 or the right-hand side of the 4? Is it smaller than 4 or left or less than? It's less than it, so I'm going to go left. Okay. Now there is a node there. All right, so I do the exact same thing again. So now I'm going to compare 2 to 3, and 2 is less than 3. So which side does it go on? The left. So this actually goes over there. Okay. All right, and now we insert the 6. 6 is bigger than 4, so it's going to go off the right side of 4. And I have a 6. Okay? So that's what hopefully everybody wrote down as the answer to drawing a binary search tree with inserting the values 4, 3, 2, 6. Everybody get that? Yes.
But then, like any node could be a root.
Well, yes, no, but sort of, but no. All right?
Sure.
What determines, in this case, which node is the root node? It's the first one you insert, right? Okay? So let's do that, all right? Let's change the insertion order, and let's do it in sorted order, okay? All right? So 4, 3, 2, 6, this is the tree that I got, all right? Now let's insert 2, 3, 4, 6, okay? So first of all, I don't have a tree yet, so we're going to put 2 here. All right, now where does the 3 go? 3 is bigger than 2, so it goes off the right. Good. 3 is right here. All right, now where does 4 go? If 4 is bigger than 2, okay? 4 is bigger than 3, so it goes over there. Got that? All right, what about the 6? Bigger than 2, bigger than 3, bigger than 4. There's nothing over there, so I put a 6 over there.
Not just like a linked list.
Oh, what did you say?
Isn't that a linked list?
Isn't that a linked list? Sure is, with a whole bunch of extra usage space because I'd never use any of the left pointers. Yeah, but that is a linked list, isn't it?
Bad tree.
Huh?
Bad.
That's a bad tree. What's a bad tree? We don't like those trees. Okay? All right. But notice the same values is over here versus over here. Okay? And if I follow that left-right rule, I can still find stuff. All right? So let's now switch it. So this is the inserting something. All right, what about finding something? What happens if I was trying to find the value 2 over here on this tree? What do I do?
You look and see if the number you're looking for is bigger or
Right.
greater than or less than.
Right, if it's greater than, equal to, or less than the value of this node right here, okay? All right, so 2 is less than, so the 2 must be to the left of this 4. So now I go down here, all right? 3, 2 is now less than 3, so I look down here. Hey, that's actually the value, so it's actually there, okay? What about 5?
So
Where would 5, if I was searching for 5?
go to the right.
You're right, I go to the right because 5 is bigger than 4. I sit on the 6. 5 is smaller than 6, so I look left, but there's nothing there. Is 5 there? No. Is there anywhere else on this tree the 5 could exist? No, really it can't be, because it has to be bigger than 4 and less than 6. So the 5 has to be, I want to say, here or somewhere in this subtree, the 5. Okay, all right, so that's finding something. We went over insertion. We are not going to do deletion until next week, because that's tricky. Okay, all right? Okay, all right, so earlier we said this was a bad tree. Okay, all right, let's make a really, really good tree. And we're going to insert the values. Hold on, I gotta think. I'm gonna make this perfect so it works out perfectly. No, that's not the number. So I want 4. Insert 6. 2, 1, 3, 5, 7. 1, 2, 3, 4, 5, 6. Okay, I think I got that right. Okay, all right. All right, let's draw together a binary search tree with those values in that order. Okay, and we'll see if I can do this properly in my head. All right, insert the 4 is right there. Okay, where does the 6 go? To the right. Okay, so the 6 goes over there. Okay, where does the 2 go? To the left of the 4. Good, 2 is going to come over there. Good, all right, where does the 1 go? Yep, it goes smaller, smaller, so the 1 goes over there. Okay. What about the 3? Right, so it's the right of the 2. So 3 is less than 4, greater than 2. So I put the 3 over there. All right, what about the 5? The left of the 6, like that. And what about the 7? The right of the 6. Hey, I got that right. Okay.
Is that in traversal order?
Hmm?
Is that traversal order?
No.
Oh no, it would be the 1, 2, 3.
We'll go over traversal order in a second. Yes. All right. So is there any more numbers that I can add to this and keep the same height? No, there's not. Okay, all right, because if I add any more numbers, what's going to happen? Well, I have to put it down here, right? And then my height would go up by 1. Okay, all right, so what I'm going to write down over here is this has a height. We have a height and a number, okay? And if I have a height of 2, and by the way, we call this a full tree, okay? A full tree is where all of your leaves are on the same level, okay? All right? So all the leaves are on the same level, which is at the very bottom, okay? All right? So this is like the first weird definition is a full tree. The other definition is called a complete tree. All right, and let me just draw a complete tree for you and see if you can figure out what the definition is. That is a complete tree. Okay? All right, so a complete tree is almost a full tree, except some of the are 1 level higher. Sort of get that? All right. Is there any way that I could have drawn this tree in 1 height? No, it's not. Okay, all right. So a complete tree, I'm going to argue, is log n height as well. All right? And search order, as long as it's complete, you have a log n search time. Okay? All right, so this is a complete tree. So that's another definition. Hopefully I got those definitions. I may have them backwards, but okay, so this is a complete tree. So let's over here write out the number of nodes based on a full tree with different heights. Okay, so a height of 2, 1, 2, 3, 4, 5, 6, 7. I have 7 nodes. Okay? All right, can anybody give me the number of nodes if you have a height of 1? So essentially, if I took out that bottom one, how many nodes do I have now? 3. I have 3. Okay? All right. What about height of 3? 15. 15? Can everybody do that sort of in their head? All right, so I have another one, 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 right? So how many on that level? 1, 2, 3, 4, 5, 6, 7, 8. 8 plus 7 is 15. Okay, got that? All right, anybody want to take a guess what it's going to be for 4? Yeah, 31. All right, anybody know what the formula is? Yeah, it's 2 to the n minus 1, okay? Notice, 3, well, that's just 1 less than 4. 7, that's 1 less than 8. 15, that's 1 less than 16. 31 is 1 less than 32. And then this one's going to be 63. Oh, sorry, that's 64. I have 63 nodes. Okay. Another thing to note, notice I had 1, 2, 3, I have 8 leaf nodes. How many interior nodes did I have? 7. Okay? So by adding one more level, I a little bit more than double the amount of nodes in my tree just by one more level. Okay, all right? So the formula for the number of nodes is 2 to the height minus 1. Okay? All right? Everybody sort of get that? All right? Okay, so now let's talk about search time. Does everybody remember the number guessing game? I have a number in my head between 0 and 100, and I will tell you low or high. Somebody guess a number. 50. The number is less than that.
30.
The number, okay, let's stop right there, because why did you say 50?
It's right in the middle,
All right, so why right in the middle?
because it has the same number on the higher end and the lower.
Yeah. Mm-hmm.
It's a binary search tree.
It's a binary search tree. Essentially, it's a binary search tree, okay? The way that I like to think about this is if you guess 50 and I tell you higher or lower, how many numbers did you just know it can't be? 49-ish, right? So you removed, so at the very beginning, you had a search space between 0 and 100. You have no idea what it is. After one guess, how big is your search space? It's half the size, because you removed the other half. Do you get that? Okay? That is the same reason why finding something in a binary search tree is log n time. How many times do I have to guess, or how many times do I divide that search space by 2 until I get to a single element? Okay? That's the idea. Okay? All right? And that's why it's log, technically it's log base 2 of the height. Of n. Okay? All right? All right. Now, anybody want to tell me a yeah but situation? So this is the height, and this is the number of nodes if it's full. Okay? But let's talk about this one. All right? What's the height of this tree?
3.
Yeah, technically it's 3. Again,
Yeah.
it's like one-off errors, but we're going to call this 3. All right? And how many nodes are there? 4. All right? If I added a 7, and then an 8, and then a 9, and then a 10, okay? How does the height and the number of nodes related now?
Well,
Practically the same.
yeah.
Practically the same. It's off by 1, but technically it's the same, right? So if I'm searching for something here, right? It's horrible, right? So this would be equivalent to playing the guessing game. I have a number in my head, and then you guess, like, is it 1? No, it's not 1. It's much bigger than that. Okay, is it 2, right? Not to pick on my daughter, but she used to do this, right? Is it 3? Is it 4? And I'm like, no, it's 65. I'm done with you, right? So previously, if you just did the divide by 2, you would guess 50, 75, and you sort of hone in a whole lot faster, okay? All right, so what does this tell you about binary search trees and their speed based on this tree and then this tree? So finding an element in here is log n time. Inserting is log n time, okay? But up here, it's not. What is it? It's O of n, okay? So one problem with binary search trees is the speed of them depends on their shape. Ruh-roh, okay? Now, I gave you these numbers so that the shape comes out like this, okay? Now, next week, or the week after, we will talk about how you can build or modify a binary search tree so that it's fast and complete, or nearly complete. Okay? All right? So we're not going to deal with that this week. Now, this week, we're just going to deal with writing the code to actually build these binary search trees and inserting the nodes in the same order that we did here. Okay? All right? All right? Any questions about this so far? No. Yeah, aren't they cool? Log n time. Okay. Oh, we didn't go over the traversal order. Okay. So the traversal order. I'm going to draw something sort of weird. This always helped, well, me when I was learning this. I'm going to pretend that this tree, I'm going to do this one. 2, 3, 4, 6 is like an island, and I'm kayaking around the outside of the island. Okay, all right, I'm going to start up here, and I wish I had another color, but hopefully you can just see this. I'm going to start up here, all right, and every single time I have like a pointer or an arrow, I'm going to sort of like, make sure there's nothing there, right? So I'm going to sort of build it like this. Okay, all right. So I kayak. Oh, a 2. There should be a pointer here. There's not. Let me just go around maybe the coral reef. Okay, all right. What this is really showing is each of these nodes has a left and a right subtree. Could have a left and a right subtree. Okay. Now, how many times do I actually pass by a point on this island? Like, let's just talk about point number 3. I passed by it going this way, right? And then I came up here, and I came down. That's a second pass. And on the way up is a third pass. Sort of understand that a little bit? Okay? So I'm passing that number 3 times. Okay? Now, number 2 is a weird one. I passed it there. I got closer to it there. I got closer to it there, all within the same. Right? Now, up here on number 4, I sort of passed it. I guess technically that would be like on my left. I passed it on my left again, and then I came back to it. So I'm visiting each node 3 times. Okay, all right? Now, how this is really going to work in the code is we're going to do this recursively. And the traversal order really determines when you print out that value. Okay? So pre-order, okay, is the first time that you visit a node or you see that node, you sort of print it out to the screen. Okay? So the pre-order traversal of this tree would be 4, 3, 2. All right, so I visited a second time, a third time, all right, second time, third time, and then I visited the 6 for the first time right there. So the pre-order traversal is 4, 3, 2, 6. Got that? Okay, all right. Next one is in-order traversal. And you can sort of take a guess. This is the second time that I visit a node, I print it out to the screen. Okay, all right. So 4, that was the first time. 3, that was the first time. 2, that was the first time. Oop, I visited a second time, so I output a 2. Coming up to the third for the second time, oop, I output a 3. Coming up for the fourth for the second time, I output a 4. Come down here, I visit 6 for the first time. I output 6 for the second time, so I output a 6, a third time, and I'm done. Okay? So the in order traversal of this tree is 2, 3, 4, 6. Okay? All right, anything special about those numbers? They're in order, aren't they? Hey, that's why we call it in order traversal. Okay? Okay? Or you can also call it sorted order because the elements are sorted. Okay? All right? And just for fun, I'm not sure, maybe on the exam I'll ask you this, but what do you think of post order? The third time you visit a node, you print it out to the screen. Okay? All right. So what is the post order traversal? First, second, third. Ooh, let's do a 2, right? Coming up to a 3, that would be the second. Third, that's a 3. That's meeting the 4 for the second time. Coming down here to the 6, second time. Third is a 6 right there. And finally, we do the 4th, okay? So the post-order traversal for that tree is 2, 3, 6, 4. Okay? All right. Anybody want to take a guess? Why is this useful? Obviously, the in order is sort of convenient because it gives it to you in order. What about the pre-order and the post-order?
Could give you the mapping of the tree.
Yeah, actually. Which one gives you the mapping or the shape?
Yeah.
Which one, the pre or the post? Shall we investigate?
The pre.
All right, so one of you, I am using the back of your homework assignment because I ran out of paper. Okay, let's do the pre-order traversal. So I traversed this tree. I outputted 4, 3, 2, 6. And now let me insert the values, 4, 3, 2, 6, into a tree. And what am I going to get? 4. Insert a 3. Well, that goes on the left-hand side. Insert a 2. That goes right there. Insert a 6. A 6. Yes, it is exactly the same order that I inserted the first time.
Wouldn't the 2 go in the left of the 3?
Oh, you're right. That goes over there. Thank you.
Yeah.
It looks exactly the same. Thank you. All right, in order traversal. All right, let's insert a 2. There's my 2. Insert a 3. 3. Insert a 4.
Just a really bad one.
Insert a 6. Is that good or bad?
Bad.
Bad. Okay, all right? This now my insertion, searching, deletion, turns out to be O of n, which is bad. Okay, all right? Now, the pre-order traversal gave me back the exact same shape. That's nice, all right? Let's do the post-order traversal. So let's insert a 2, okay? Insert a 3, insert a 6. No, I didn't do that. Insert a 6. And now insert a 4. Is that useful? Not really, that's not useful. It's not useful. Is that a full, is this one a full tree? No. Is it complete?
No.
Now I might want to update my definition of a complete tree, but whatever. Technically, how many leaves are there in this one? Technically, there's only 1 leaf, okay? It is not complete. And the reason is it could be shorter, okay? This has height 3, 1, 2, 3. But if you notice, this one has height 3. This one has height 2. Ooh, excellent. So this one's faster than both of these other ones, okay? Technically, this is the same speed as that, okay? All right? There's no real use for the post-order traversal. It's just one of those. It's there, right? There's 3 options. It's easy to figure out which they are. First one's great, second one's great, third one's useless. Okay, so that's the post-order traversal. Okay, all right, you ready to do this in code? Are you sure? All right, any other questions about trees? Did the video cover anything else? Okay, I'm going to make essentially from complete scratch this binary tree code. And you said the homework assignment doesn't work? What does it do? There's just nothing there? All right, I'm going to have to go deal with that. All right, moral of the story is set up the homework the night before. I didn't do anything different than I did in previous weeks, other than set it up at 12:58. All right, okay. So we're going to code, I'm just going to call this bst.py because we're in Python, not C++. And let's create a class called bst, okay? All right, now, oh, I guess since you can't do the homework assignment, you can't do the lab. That's a fun problem. Okay, all right. So I think what's going to happen is I will put off the lab to be due Friday night, okay? So that you can watch this video once the homework gets fixed after this class, okay? All right? Actually, let's go take a look at the homework assignment right now so that you can see where we're trying to go towards, okay? Oh, and by the way, homework 6 and lab 6, it is really the exact same write-up. And yes, I know there's 2 lab 6s. We're not going to do anything about that. There's just going to be 2 of them. Maybe I'll rename last week's lab. Okay, so for homework, what I want you to do is implement a class called simple BST, all right, with a couple of functions in there, likely in the next hour and 15 minutes before lab is done. I will probably implement all of those, okay? So that's not too bad, okay? All right, we'll see if we get all of them, okay? So also for a homework assignment is I have another class called KVBST, okay? And this is a binary search tree, but do I still have this up here? Yeah, all right. So here we go. So this is still running. So here we were doing a binary tree. Why does it look fuzzy to me? I don't know. We have a binary search tree, all right? And we can insert values into trees. We can see if a value is in there as well. But the KV really stands for key value, all right? So rather than only storing, and by the way, notice up here, I have a left pointer, a right pointer, or left child, right child, and then a value, all right? Now I want to store 2 values in each node, a key and a value, okay? And the idea is I want to store something by key, all right, the value. I also want to look something up by key. Okay, all right, that's why we call it a key value store. They say, hey, store this. I don't know, what's a good example of a key value store? All right, so all of you have UNDID numbers, and you all have email addresses. And I need a really fast way to go from ID numbers to email addresses, okay? So what I do is the key is your ID number and the value is your email address, okay? And I might want to change that value sometime, okay? And because it's in a binary search tree, I can access your node in log(n) time if it's complete, okay? You get that? All right? The other way to do it is I could have a list of pairs of things, and then I would have to check the first one, the second one, third one, and that turns into O of n, okay? So storing that data in a binary search tree, as long as it's complete or full, allows me to insert, retrieve in log(n) time, which is nice, okay? So this second class, all right, the KVBST, is really a copy of the simple BST code, except each node now stores 2 pieces of information, all right, rather than just 1. And we're always dealing with that key, all right, and sometimes returning the value, okay? Now, since I just wrote this at 12:45, I don't have all the functions in there, but it's going to be in the code, okay? There's just a couple others because we can insert, we can find, you can also get a value from the key value store by key, all right? And you can also set a value by key, okay? So those are just 2 extra functions for that, all right? All right, now because we actually want to use this binary search tree and KVBST for something useful, I came up with a use case for this, and this is called word count. Okay? I will this afternoon. I don't have a solution for this yet, but it shouldn't be too bad. I will put the example output at the bottom of this document. But the idea here is you're going to write a Python program that uses your KVBST to count the frequency of words in a document. Okay? So the key is going to be the word. The value is going to be the number of times you saw that word. Okay? All right? Based on 155, does everyone remember how to open up a file? Anybody? Okay, so what is the code for opening up a file? There's two ways to do it.
Was open.
Yeah, technically use the with. I know, the with is the better thing. If you don't know how that works, just go Google it. It's all over the internet. But technically it's just f is equal to open. You give it the file name. I guess technically you have to give it a parameter that says this is a text file, not a binary file. And then you can read that into a big old string. Beautiful. Okay, all right? And then you split the string, which is the contents of that file, on spaces to get all the words. All right? And then you loop through all of those and you put stuff into the KVBST. So to get that idea? No? All right, well, next week, next Monday, I'll go over that in a little more detail. I think I did have this due on Sunday, October 20th. I don't think I changed that. That's still wrong. But that's the idea. So what I want the output to be is output the number of times each word was seen in the file using the KVBST class. Oh, I should have mentioned in here, in alphabetical order. So I want to see how many times apple was used in that file before zebra. Okay? Now, based on our traversal methods, what traversal method do you think we should use to get things in order?
In order.
The in order traversal method, exactly.
Wow.
Hey, how useful. Okay? All right. There may be a structuring problem because you're going to probably insert the nodes as you see them, and it might not be completely balanced, but let's just ignore that problem. Okay? I guarantee you the text that I put in your repositories are not the dictionary. It is not in alphabetical order. I think I gave you, Moby Dick, all the works of William Shakespeare, and another random file that I just happen to have the text of, which is sort of cool. We'll use this for next semester's big data mining, because we'll analyze them in more detail. Okay? All right? So that is the homework assignment. Okay? I do have PyTest. There's two tests. One for the simple BST, another one for the key value BST. I don't have any unit tests for word count because that's practically impossible to do. So I'm going to have to check those manually. All right, simply those are the three files you should submit. And your class activity or lab activity, I'm going to change this right now, is I want you to implement the insert function and the length function in the simple BST class, which we will likely just do now. Okay, all right? And then for the homework, it's everything. Okay, all right? Okay, is that sort of clear? So I'm going to start this from absolute scratch. Oh, that was the solution. Good thing you didn't see that. Which is my other one? No. Oh, that's C code. There we go, class BST. Okay. All right, so just like our linked list, we're going to define a node class inside. Okay, and I'm going to write a little bit fast here, since this is sort of boilerplate. Slots is equal to value left, oops, and right. Okay, and def, init, self, value left and right. By the way, what do we call this? That's rather boring. All right. So this sets up what a node looks like. Okay. And now we have our constructor for the entire class. Okay? All right. So what do you think we need to keep around so that I have access to this, to any of these trees? This one, all of them. I need to keep a pointer to the top node. Got that? All right, and we're going to call it the root. And yep, it's at the top. Okay, so we'll have self.root, underscore root is equal to none at the very beginning, because at the very beginning, there's no nodes there. Okay? All right? All right, what function do you want to implement now? Insert. Okay. Insert self value. Okay. All right. Ideas. How did we insert nodes? We actually got pretty good at it.
You have to create a new node.
Okay, we got to create a new node. And then the question is, where do we put it? Let's try to insert, just talk about what I would do for inserting the node 1. Did he implement this code in the video?
Next class.
Next class, yeah, thought so. Okay. All right, let's walk through. If you notice, if we rewind this video, I talked inserting nodes in a very explicit way. What did I do? Remember?
Check to see if it's less than.
Check to see, right. So what I'm actually going to do is I'm going to first look at root and see, does that have a node associated with it? And by the way, I'm walking through what the code looks like, by the way. If there is no node there attached to root, what do you think I'm going to do? Create one and attach it to root. Done. Right? It's the first node. All right. So this is very similar to the linked list situation. If I don't have a linked list, I insert a node and then fix my head and tail pointers. Okay, sort of similar to that. Otherwise, I have a tree and root points to a node. All right, what question do I ask myself looking at that node?
The value is less than.
Right, if the value is less than, well, or equal to, or greater than that node. Okay, all right? And what do I do if it's less than?
Put it to the left.
Okay, I put it to the left, right? I'm going to change that wording a little bit, and I'm going to say I'm going to go left. Okay, now what do I do?
Check that node.
Check that node, okay? And if I'm going to insert a 1, I'm going to go left. Okay? Again, I'm going to check that node, and then I'm going to go left. Oh, there's nothing there, so what do I do? Insert the node, okay? All right, now if you noticed, I asked myself, is it less than, or greater than, or equal to that node 1, 2, 3 times, okay? Now, another thing I want to discuss here is 2, 3, isn't that a binary search tree? Mm-hmm. Technically, isn't 2 a binary search tree? Mm-hmm. Right? So this is a recursive data structure. All right? So every single node's child is also a binary search tree. Okay?
Subtree.
It's a subtree, right? But it's also just a binary search tree, okay? That happens to have a parent to it. Okay, all right? And once you realize that, you'll think, oh, if I have a recursive data structure, I could use a recursive function to traverse that data structure. And it turns out to be super, super simple if you think of it like that. Okay, all right? So what we're going to do, now, at the very top, it's a weird one-off, right? I'm really going to look at root, and I'm only going to use that once, okay? So many of these functions in this solution are going to look pretty similar in that we have a regular function. I'm going to call this insert. And then we're going to have another one that is a sort of private version of this. Okay, but I'm going to give it 2 parameters. And the first parameter is going to be a node, and the other one is going to be a value. Okay, all right? So, and our global one, the insert, the main one, this is where we're going to do that comparison with root. Okay, all right, so if self._root equal none, anybody want to say what we do? Before I take a guess. So the tree is completely empty. Sorry, what was that? Yep, self.root is equal to node, right? I'm going to create self._root is equal to node. All right, now I have to sort of fill in all these things for the constructor up here. Notice there is no defaults. Oh, do you want to do defaults or not? Should we do defaults? Actually, I'm not going to do defaults, just because it forces you to think about what those things are. So what value is that? Well, it's whatever they said. Okay. What is the left pointer or left node? None, because there's nothing there. The right one? There's none, because there's nothing there. Okay? All right? And that is it if root is nothing. Oh, and I forgot this. You have to do the self.node. Okay? All right, so that handles the sort of base case in that there's nothing in the tree. Okay? Else, what we're going to do is we're going to call self-insert, okay, with the node, all right? And this is going to be self.root, comma, value. Okay? All right, now, in this else case, what is the value of root? Is it none? No, it's not. It's a real node. Okay, it's a real node. Okay, so this insert function is going to take a node, all right, that exists, all right, and a value, and create a node in that subtree. Okay, all right. So anyone take a guess what we're going to do inside here? What did we do if I was trying to insert the value 1, and now I've been given this node?
Check if the value is less than or
Right, I got to check the value. If it's less than the node's value, I have to go left. Otherwise, I have to go right. Okay, and that's exactly what we're going to do. All right, so we'll do an if statement. So if the value is less than node dot, what did I call that? Value.
Do you have to do less than or equal to, or just less than?
It's up to you. One of them will have a equal sign to it. So we'll do the same thing for the other side. All right, and one of them will have the equal. Okay. Where do you want to put it? Let's put the equals on the right. I don't know. So if the value is less than node.value, it goes on the right. Okay. Okay. So let's go back to our picture here.
Isn't it to the left if it's less than?
Yeah. Isn't that exactly what I just typed? Thank you. That's exactly what I just typed. That's exactly what I just typed. All right. All right. So we go to the left. All right. And notice we have another tree over here. Okay. Now, if I was down here and sitting on this 2, 1 is less than 2. But what is over here on the left-hand side? Nothing. So in that case, I need to create a new node. Okay. What about up here? If there was a node there, do I create a new node yet? No. I then go left. Okay. All right. So we have another if statement in here. So the if node.left is equal to none. All right. Now we're going to create a new node. So node.left is equal to self.node value comma none comma none. Okay. Is that clear for everybody? And yes, this is a lot of code to write before I even unit tested anything. But the problem is there's no way to test this until I sort of wrote it all. And then we'll have to deal with any bugs that I wrote. Okay? Okay, so if it's not equal to none, what am I going to do? I'm going to go left. And if this is recursive, this is now my recursive call. I'm going to call self._insert with node.left and value. Same sort of reason up here. If it was none, I do this. Otherwise, it's a real node, I do that. Same situation right here. If it's none, I do this. I create the node. Otherwise, left must be your real node, and then we're going to insert on that subtree. Okay? All right. So that's the left-hand side, and we just need to be symmetric here. And I'm just going to do an else. Yeah, so either it's on the left-hand side or the right-hand side. So if it's not on the left, it must be on the right. Okay. You could conceivably make a binary search tree that doesn't have any duplicate elements in it.
I was gonna say, what would happen if on that one we put a 4?
Yeah, if you put a 4, well, there it depends. Do you want to put the 4 on the left-hand side or the right-hand side? As long as we're consistent, it's perfectly fine. Yes. Okay. But where would the 4 go if it's always on the right? Well, it would go over here. 4 is less than 6, so it would live down there. Yeah.
But then when we look for 4,
Mhm.
will it output 2 of them, or?
Well, when we do the find, it'll find the top one. It'll find the top one.
But then what's the purpose of second 4?
If you wanted to store that there was multiple 4s. Okay?
But we can,
But this is not what I want you to do for the KV BST. Okay? For the KV BST, what I want you to do is don't insert that key a second time. And by the way, there's a difference between insert and set. Insert only inserts if it's not there already. It throws an error if it's there already. Okay? Set only changes it if it is there. If it's not there, it throws an error. Okay? So another way to think about this, if we just want to have a binary search tree that doesn't allow the same value twice, this is in the code where we would put that, right? If the value is less than, we do this. Else, if the value is greater than, we do this. Otherwise, don't do anything because it must be the same and we're not going to add a second time, okay? Another option is if we wanted to be sneaky about it, we could store a number associated with each node with how many times that was inserted. Okay? Now that's a little bit more space efficient because then you can easily ask how many 4s are in the tree, and then you just find the 4 and you see, oh, there's 5 of them. Excellent, there's 5 of them. But your tree doesn't get that much larger. Okay? All right? Again, that's sort of similar to your key value binary search tree. Okay? You're just going to use a binary search tree in a key value form and store a number as the value, and then you're going to manually increment it. Get the current value and then set the new value to update the count. Okay? Okay. So we're just going to assume everything else is going to go on the right-hand side. Okay? And what's sort of nice about the code is it's pretty symmetric because it really is that, except rather than lefts, we just look right. Okay? And I have a 98% confidence that that's correct. All right, what's the next? All right, next, let's do length. Okay, length is going to be the number of nodes in the tree. Okay? All right, so coming back to our binary search tree, what can I do to find out how many nodes are in the search tree?
Keep track of height.
Okay, keeping track of inserts is a great answer. It's too easy, we're not going to do it. All right? Preferably, let's walk the tree and keep track of the nodes as we walk the tree. Okay? All right? Now, here comes the fun way. How many nodes are in this tree? 4. Okay. How many nodes are in that tree? 2. How many nodes are in that tree?
1.
Okay. So, what's 2, this subtree, plus this subtree is 3, plus its parent? Well, 2 plus 1 is 3, plus 1 is 4, right? Okay? So what we sort of did right there is we defined the number of nodes in a tree as the number of nodes in a subtree. Okay? So I'm looking at this tree. How many nodes in this tree? Well, it's 1 plus however many nodes in this subtree plus how many nodes in this subtree. Right? Okay? So, yeah, the code becomes super simple once you start doing this recursively, all right? Now, this is the first time that we've done a recursive function that's essentially two-dimensional, right? Typically in a list, you just take one element off. Now we're actually making 2 recursive calls in one function. That's allowed, and it works really well. Okay? All right? So again, we are going to make a recursive version of this length function. So def, we'll call this myLength, and self and node. Okay? All right, anybody want to take a stab at what this is going to be? So we're going to give it a node. All right, so we're going to give it a node 4. And what is the number of nodes in this subtree? I just told you this. In this subtree, right, the 4, it's that plus 1. Right? Okay? All right, so, yeah, let's just write this. So I'm just going to do a return statement. Return my length of the left subtree, so that's node.left, plus, oops, sorry, I need a self there. Why is it super grumpy? Okay, I'm not sure why. Plus self.my node.right plus 1. Okay? Can everybody see that? Is that big enough? Okay? Does this make sense to everybody? The number of nodes in a tree is however many nodes in the left subtree, right subtree, plus 1 for itself. Okay? All right, anybody want to yell at me? This is a recursive function? There's no base case. All right, what do you think the base case is? When there's no more subtree, yeah. So if I'm sitting on this 2, all right, it's going to, well, there's 2 ways to think about this. Either I'm sitting on this 2 and I notice that the left subtree is none, and I also notice the right subtree is none, then I don't have to recurse. Okay? Now it turns out in this case, could I recurse? So if I recurse, I'm going to send it down the left node, which in this case is going to be none. Okay? Which actually for the code is rather sneaky. So because I never am looking at left or right, if I can detect none first, I can just detect if node equal none, what do I return? How many nodes in a tree that doesn't have any nodes? 0. Okay? And that's a little sneaky because it works for both the left and the right. Okay? So if you're online and looking at other people's binary search tree code, you might see them do this slightly differently. You might have some if statements in there. I really like this because this is really sneaky, because that gives you the number of nodes in the entire tree. Okay? All right, so now let's fix this length function up here. What does this need to do? This is very similar to what we did up here. Actually, it's so similar, I'm going to copy and paste it. Ooh, actually, I take that back. It's even simpler. We could do it as a one-liner. Anybody want to take a guess? Notice this myLength function has nothing to do with root. So probably we've got to do something with root. When we were inserting something, none of this code had to do with root, because this is the code that sort of traverses down. Okay? The spot that dealt with root is up here with the top, the public insert. Okay? All right, so what do you think this is going to be? Anybody have any ideas? Can I start you off? What's that? Yep. Return self dot underscore myLength. All right, and what do I give it? Huh? Yeah, the root. Exactly. Self dot underscore root. And that's it. All right? That's going to start it off at the very top and then do all the fancy traversals all the way down. Okay? Now, this is the first spot that now we can start to see if any of this works. Okay, so let's say A is equal to BST. All right, and let's just do a print of len of A. Okay, and then we'll do A dot insert the value 5, and we'll also print the length of A. And let's just do that again. Sure, let's do a 6. Okay, all right, so what should this print out to the screen when I run this? Ooh, I gotta save it first. Wow, there's a lot of typing and no saving. I create a binary search tree. How many nodes are in the binary search tree? 0. I add a node. How many nodes are in the binary search tree? 1. And all of you thought that computer science was complicated. All right, we insert another node into the binary search tree, and now how many nodes are there? 2. All right, so hopefully this prints 0, 1, 2. Anybody want to take bets? Oh, man. I should have bet somebody money that I had a syntax error. 0, 1, 2, it worked. I'm really proud of myself. I never looked at my cheat sheet once. I might have written this like a dozen times over the years, but that's okay. Oh, I had to write this code in C++ for my Amazon interview. I got this right. Then they asked harder questions, and I think I got those wrong, because I didn't get the job. All right, so what do you want me to write next? Do we have any confidence that 5 and 6 are actually in the binary search tree? No, we don't. Technically, if I wrote a unit test that did this, some of you would be just not actually store anything. Okay, I know you'd be really sneaky. Okay, let's do print. So if I want to print A, at the moment this isn't going to do anything properly. It's just going to say, I don't know how to print this object. Okay, let's implement that, because this is very useful for debugging. Isn't it str? Yeah, okay, good. I don't have this in my notes, so here we go. Okay, so now I want to return a string, which is all of the values in this binary search tree. Okay, and this is the first really good example where we love Python and we hate C and C++. Because in Python, this becomes embarrassingly simple. All right, does anybody see any code on the screen that might be useful? What?
The same recursion function, but with print.
Yeah, it's actually the length function, the same idea, except now we're just going to be returning strings rather than returning plus ones. Right? Yeah, okay. So let's do that. So str, I'm going to again have to make another one. Actually, it's just return. Let's see, what do we want to call this? Self dot underscore, maybe just st. That's a horrible name, but that's all right. And we're going to give it self dot root. Okay, and then in the recursive function, all right, we will honestly just copy and paste that and then modify it a little bit. Okay, all right, so what do we print to the screen if the node is none? Nothing. But we have to return the empty string. Okay, here comes the fun part. All right, otherwise, how do I want to return or print? Let me just modify this a little bit. This line.
Self dot underscore st, and then in parentheses, node dot value dot length.
No, so remember, I'm always passing down the node because it needs to traverse. Okay, all right. I'm going to print out the value over here. Okay, and actually I'm going to call the str function on node.value. Okay, that converts the value. If it was an integer, it'll return that to a string. Again, this is helping Python along. I just want that as a string. And now, oh, that's not s. That just need to be st. Okay, this function either returns a string or a string plus a string plus a string, which is a big old string. Okay. Now, for readability, I am going to put in some commas. Like that. And now, let's just run that. And we get comma, comma, comma 65. That's not very pretty, is it? Okay, well, how many nodes are there? 2, right? How many numbers got printed? 2. That's not so bad. All right. Anybody want to suggest I change some code just to sort of feel this out a little bit? Ooh, excuse me. Here, let's stop printing the lengths. And we'll just insert some more values. All right, we're going to insert the values 1, 2, 3, 4, 5, 6, and then print it to the screen. And I get a whole bunch of commas. But I do get 6, 5, 4, 3, 2, 1.
Do we fall off the tree and then just...
Did we fall off the tree? No, we did not fall off the tree. We want to change some code here. At the moment, it is outputting all those nodes. Actually, off the top of my head, I don't know a sneaky solution to get rid of all those commas. And want to take a guess what traversal method this is?
In order, but flipped.
No, it's not. Close, though. Really close. When do we print out the value of the node? This is really hard to think about. Huh? At the end. It's actually the third time. It's the entire tree on the left, the entire tree on the right, and then the value. So technically, it's the third time we sort of see this, all right? And what's sort of cool about this is what happens if I just move this to the middle? And put the commas in the right spot. Okay, and now I have to run it. Well, all right, what's going on with my Wi-Fi? That was a super long delay. Now I get 1, 2, 3, 4, 5, 6. Okay, that is now an in-order traversal. Okay, what do you think we have to do to get a pre-order traversal? Yeah, put it before. Yeah. Okay.
You still have commas.
I still have commas. All right. Anybody have any ideas how to get? And why do I have commas there? Extra commas. Because it's printing out a comma even if it's not a subtree. If there's a null pointer, it's still printing out a comma for that empty subtree. Okay? That's sort of the reason. Yeah. Okay, all right. So this sneaky way of having it sort of recursively and then none is equal to nothing is sort of now starting to bite us a little bit. Okay, all right. Anybody have any other ideas how we could fix this? I know of two ways. The first way is we just detect node left, node right, all right, and then do something particular with those strings. The other thing is to, I don't know, I'm just going to do this and see, is to change the return type completely. And that is, how about st does not return a string. This returns a list. And then in this function, we put the commas in. Okay? Because the idea here is now, well, putting an empty list on an empty list just gives me an empty list. It doesn't have any commas. Okay? So just to see if this works, I'm just going to convert that to a string. All right? This is going to return an empty list. And now I'm going to get rid of those commas. All right? And now st is going to be a list. St is going to be a list. And that is going to be a list of a single element. I don't know. I don't have the solution, so I'm not sure if this will work, but it might. Can only concatenate list, not str2 list. Wait, but what? Oh, I changed that. That's self dot underscore str. Yep. I need to stop typing so fast. That's what I really meant. Object has no attribute left. Oh, hold on a second. I messed this up. This needs to be bracket, oh. No. You're seeing live debugging right in front of you. There we go. Yay. Okay. And now I get the list 1, 2, 3, 4, 5, 6. Actually, let's just keep it just like that because it looks really good. Because when I converted a list using the str function to a string, it put the brackets and it put the commas in there. Hey. Okay. All right. What does this look like if I were to draw this out? 1, 2, 3, 4, 5, 6. Right, it's actually a linked list, okay? So let's play with this a little bit. Let's completely change the order. Let's put the 6 and 6, 4, 1, 2, 3, 5, okay? Now how is this going to print? The exact same. Okay? Now, the internal structure is now completely different. Okay? Which node is the root now that I have the 6, 4, 1, 2, 3, 5? Which node do we insert first? The 6, yep. So the 6 is now the root. Before the 1 was the root, all right? So this is a little bit more balanced. Oh, shoot, I didn't give you the definition of a balanced tree. Okay. All right, a balanced tree for all nodes, the number of left nodes, well, let's just do it this way. Absolute value minus the number of right nodes is less than or equal to 1. Okay? All right, so you subtract. You find how many nodes are on the left-hand side find how many nodes are on the right-hand side, and you make sure that that's less than or equal to 1. Okay? You have to do the absolute value because you don't really care which one's bigger. Okay? All right? So this makes sense to everybody? Okay? So let me just draw some trees, and you tell me if they're balanced or not. Is this tree balanced? Okay, so let's start here at the 4. How many nodes on the left-hand side? 2. How many nodes on the right-hand side? 1. What's 2 minus 1? 1. 1 is equal to 1, so we're good. All right, now, for all nodes, all right, so we recursively check down the children. All right, the 3 node. How many nodes on the left-hand side of the 3? 1. How many nodes on the right-hand side of the tree? 0, right? What's 1 minus 0? 1. According to my definition, that matches. All right, what about the 6? 0, 0, 0 minus 0 is 0, so that works too. So this tree is balanced. Okay? All right, what about this next one? 2, 3, 4, 6. All right, what's the left tree of this 2? 0. What about the right tree? 3. So is it balanced? No. 3 minus 0 is 3. 3 is not less than or equal, so this is not balanced. Okay, what about this one? Same reason, right? This top one fails, okay? Now, if I'm looking at this subtree, is that one balanced? 3, 6, and 4. No, because the 3 has a 0 over here, right? 0 nodes over here, but I have 2 nodes over here. 2 minus 0 is 2, and that violates the property. Okay, all right? What about that tree, a 6 and a 4? That follows. Okay, all right? Now, the definition of balanced for all nodes in the tree, this holds. Okay? I think on the homework assignment, I didn't give you that as a function. But again, recursively, life is easy. Okay? All right, 233. Any other functions you want me to implement? Oh yeah, let's do find. All right. How do we traverse the binary search tree? Using the same way we've done it for the other 2 functions. Okay, we have one function, the find function, that, and we're going to take a guess what this is going to do. You can probably guess and get this completely right. Yeah, if it's looking for a specific thing, we're going to call a recursive function. All right. So return self._myFind, and we're going to give it self._root, and we're going to give it, oh, I have to find a value. I'm going to call it needle. Needle in the haystack. Tough crowd today. All right. We're going to give it needle. And then now def underscore myFind. Let me do a self needle. Okay, help me out. All right, what's going to be inside of here? I'm not going to write any more code. No, we got a seg fault. We're going to get a problem with that. Right? Yeah, if the node is equal to none. Oh, I forgot to do that actually. Node. Yeah, so that's the base case. If node equal none, then what do we do? Yeah, return false. Okay? Can a needle be in an empty tree? No, because there's nothing in it. Okay? All right, so we'll return false. All right? Otherwise, if what? And now what you said before, what was it? If Yep, if no.value equal needle, what do we do? Return true. Good. Okay? All right, keep going. So now we are in the situation where I have a tree, and I'm looking at the top one. Let's say I'm looking for a 1. This node is not none. This node is not equal to 1. And now what do we do? I need to go left. I need to start deciding, am I going to go left or am I going to go right? Okay? So, yeah. So if needle is less than node.value, what do I do? Yeah, check the left side. Really, it's whatever the left side returns. That could be true or false. So this is just going to be a return self._myFind with what node? Yeah, node.left. Good. And we have to send down the needle. Okay. And let's just do an else, and we just have to go on the other side. Copy, paste, right. Did I spell that right? Yeah. Okay. And what happens if node.left is none? Is that going to cause a problem for us? No, it's no problem whatsoever. It's going to call that with node is equal to none, none is equal to none. Okay, return false, it's not there. Okay. All right, shall we try it? Let's print a.find 2. True. Good. It was there. Okay, let's find 22. No, it's not there. Let's try 6. True, because it was there. Okay, all right. Just for fun, let's make a really bad tree and see if it still works. So we're going to insert them in sorted order, which is going to make a linked list. Okay, and we'll still see if it can find 6. Yes, it can still find 6. Can it find 1? 1 is going to be the root node. Yep, and it can still do that as well. Okay, so the code for most of these functions is going to be something like this. You're going to have a function that just calls a recursive function that it's then recursing down and traversing the tree to either try to find something. For the homework, since we have get and set, those are obviously going to change values or return values. What's everybody's confidence on this? Yeah, you got to try it? Are you telling me you want the homework assignment to be due Monday night rather than Sunday night? It's a laugh. Yeah, okay. We'll make it due Monday night. Okay? And come with questions on Monday to Monday's class. Okay? Okay. I will have lab due tomorrow night. All right? And I think, yeah, it's going to be, well, the length function and insert. All right? What? Which I practically did, so you just have to type those out. Okay? In your homework assignment, there is PyTest. So if you type PyTest, it'll run the unit tests on that. Remember, you can type PyTest and then one of the test file names, and it will only run those tests. There's 2 testing files in the repository. By the way, here is the code, which I will figure out. Actually, somebody stay by and let me debug why it's not working. But this is the KVBST, and I already filled in the function names. You just have to fill in what all the functions do. And then here's the unit testing file for this. Also, here is simple BST. Similarly with, oh, it looks like I left some of the node stuff there. You have to add all of these as well. So num leaves, let's just talk about that. Oh, and height. These are not much code, but not exactly trivial either. Think about num nodes. Let's just talk about this. I want to return how many nodes are leaves.
Doesn't have,
So a leaf is a node that doesn't have two children.
so if node left and node right equal none,
Yep.
counts as a leaf.
Is what?
A leaf.
It counts as a leaf, and then it probably should return 1.
Yeah.
Okay? If either of them is not none, what do we do?
Go left or
Yeah, go left and go right. Okay? And it's perfectly fine to go down a none. That should just return 0. See what I mean? Yeah. Okay? All right? So you might have to draw out some trees and sort of build them down in the bottom to try to figure out how to, verify that works. All right, remember in that linked list, if you insert the values in order, 1, 2, 3, 4, 5, 6, there's only one leaf. Okay? If you add values so that it's a balanced tree, all right? What was that? 4, 3, 2, 6. No, that was the wrong one. So 4, 6, 2, 1, 3, 5, 7. Sorry, that's what I'm talking about. This one, right? How many leaves are in this one? 4, right? So feel free in the bottom to sort of test that out to make sure it's giving the right value. Okay? Last one. How would you do height?
go down
Uh-huh.
till left and right is none.
Okay.
I actually don't know.
Yeah.
It could just go to the right and then that would be none.
Okay. All right, let's talk about this tree right here. Can you come up with some recursive rules if I'm sitting on the 4 to give me the height of the tree? And remember, recursively, we are probably calling ourselves on a smaller version of the tree. All right, what's the height of this tree, just with the 2 and the 3? 1. What's the height of this tree over here? 0. Okay, all right, what's the height of this? Well, why don't we find the height of the left subtree and the height of the right subtree, and what do we do with those numbers? We have a 1 over here, we have a 0 over here, and notice the height of the entire thing is 2 because there. What's that? Yeah, you got to compare them, right? So we find the height of the left, we find the height of the right, and we use the bigger number. And we return that plus 1. Because 1. Do you get that? All right, let's talk about it over here. All right, so this is a linked list, 2, 3, 4, 6. What is the height? It's 3. So we're sitting at the 2. We call the height of the left tree. What's this height? 0. What's the height of this tree? 2, right? So now I have 2 and 0, but 2 plus 1 is 3, 1, 2, 3, right? What did this one do? The exact same thing. Same thing, same thing, right? What's the height of this? 0 and 0. So you do have to detect that and don't add 1 because the height of that tree, to me, is 0, not 1. Okay? All right? So there's unit tests in there for that, all right? So please work on this over the weekend. Do you want extra credit if it's done on Sunday?
Sure.
Yeah? Okay, all right. I'll give extra credit if it's committed by Sunday night and all the unit tests work, okay? Otherwise, it's just regular homework is due Monday night. Similarly, all the tests as well, okay? All right. See everybody next week.